Okay, good morning, everyone. Welcome to the second day, morning session. So the first talk will be by Marco Robalo from Institut de Mathématiques de Jussieu, Paris. He will talk about the Darboux stack of a -1 symplectic Artin stack.
So thank you very much. Thank you very much, the organizers, for this conference in such a nice place. It's really pleasant. So I will report on some ongoing work with Benjamin Enyon. So this project started a few years ago with Benjamin and Julian Austin. There are two preprints on arXiv that kind of set up what we are doing here. And I will start by explaining a little bit this story, and then I will get more precisely to the Artin case, okay? So, so this part one. Maybe some people in this room already saw this talk many times, so I will repeat the history. And for what I want to explain today, the story starts by fixing a tricalabial over C. And the goal is to study the moduli of coherent sheaves on Y, which I will simply denote by X curly X like this. So, so this story goes back a long time in enumerative geometry. You can think of this as ideal sheaves. Inside this moduli space, they're all ideal sheaves corresponding to curves. So describing the geometry of this moduli space is somehow describing the geometry of curves inside Y. But for the purposes I want to discuss today, the story starts around the year 2000 with Richard Thomas that observed that there is a symmetry that exists on the deformation complex of a coherent sheaf. Of a point in this moduli space. And the symmetry, so first of all, what is the deformation complex of this moduli space? I'll denote it this way. And this is just some kind of Rm from E to E with a shift by 1. So this is just a complex. You can think of this as the tangent complex of the point E inside the moduli space. And what Thomas observed is that the cohomology on degree 0 of this complex is actually isomorphic to the cohomology in degree 1 dualized. So there is a duality going on here. You can think of this as a space of deformations, and this is a space of obstructions. So these things are in duality. And this thing comes from the Serre pairing plus the Calabi-Yau condition. And essentially, around 2011, Pantev, Bertrand, Vaquier, and Vizozzi reformulated this pairing in terms of something they called a shifted symplectic structure. So, in other words, for the purpose I want to say today, is that this pairing on cohomology can be seen as a quasi-isomorphism between the deformation complex dualized with the shift by 1. So if the shift was not here, this would be something you think of as a symplectic form. With the shift, this is called a shifted, a -1 shifted symplectic form. So, and since the moment they understood this, the subject kind of opened up many different directions. But before explaining, going further in time, let me just give you an example. Actually, the simplest example of such a gadget. The simplest example would be, let me take U to be a scheme. And in this example, I'll just take A1. So everything is happening over C. okay, A1C. And let me take a function on U, which is just x to the cube. Then I can look at the critical points of this function. So this is just as a scheme, this is just C x divided by the derivative of f. And the interesting thing is that if I look at the deformation complex of this scheme, the Illuzi tangent complex, what I find is a two-term complex, which is the tangent of U restricted to the critical points, the cotangent of U restricted to the critical points, this in degree 0, this in degree 1, and here I find the Hessian, which is just multiplication by 6 times x. So the fact that the Hessian is symmetric tells me that if I dualize this complex, when I dualize it, this piece in degree 0 remains in degree 0, the part in degree 1 becomes in degree -1, so I get essentially a copy of the same complex, but with the dual of the Hessian. But this Hessian is symmetric. So what I'm telling you just here is that the symmetry of the Hessian gives me a quasi-isomorphism between this complex and this dual with a shift. So this is the simplest example you can think of. It's a -1 probably. I made a mistake here. Yes, it's -1 here also, right? Yeah. So this is the simplest example, or the simplest family of examples, because every time you have something smooth in the function, the critical points will always have such a deformation complex, will always exhibit such a symmetry. So let's move a little bit further in time. Around 2013, Braff, Boosi, and Joyce showed that any such stack or any such scheme or stack that admits a -1 shifted symplectic structure is locally of this form. Yes? A family? No, no family. No family. No family. And so if X is a -1 shifted symplectic derived scheme, then Zariski locally is symplectomorphic to the derived critical points of some function f on some smooth scheme U. So if I take a scheme, I have Zariski locally. If I take a stack, I have to change the topology here. If I have a Link-Mumford stack, I can have it all locally. If I have an Artin stack, I'm going to have smooth locally of this form. And so the moment we have this theorem, we have also to realize that these models are not unique. For instance, already if X is our critical points of X to the cube, to start with, it's already of the form critical points of something, but actually you can see that I can just add a quadratic variable, and this becomes a function on A1 times A1. And because this function is Morse, I didn't change the critical points. So I have some ambiguity that goes on every time I add an extra variable and the quadratic function. So there is this quadratic ambiguity that is going on here. So, and this is the starting point of the story I want to tell. So let me start by making here on the board some table. I'll try to explain what we want to do. So the moment we know that every such gadget stack, for instance, the stack of coherent sheaves, is locally of this form, we can try to take some local invariant that depends on a function on a scheme, and we try to globalize it to some, so here I have something which is -1 shifted. And here I have a local model. And since I can glue these things to get X, I can try to exploit glue information of F to get some information on F. And of course, there will be some obstruction. A priori, there is no reason that there is no obstruction to do this. So let me give you an obstruction that we just saw here is that whatever our invariant is, it has to solve this quadratic ambiguity. So let me give you a first example to get an idea of what is going on. So the first thing, one thing I can extract from such a function on a scheme is just what is called the Milnor number. Which, if the function, so as an example, if f has isolated singularities, this Milnor number would just be the dimension over the complex numbers of the Jacobian ring. So I take all the variables on U, I take coordinates on U, and I divide by the derivatives of f with respect to these variables. I get a ring, I take the dimension over C as a module, and I get a number. This is called the Milnor number. In case I don't have isolated singularities, it's more complicated. We'll see next. And there's a theorem by Behrend, that explained to us, this is around 2005, if I'm not mistaken, maybe a bit earlier, maybe 2004. That explained that because the Milnor number of a function and the Milnor number of a function plus a quadratic variable are the same, this dimension of the vanishing cycles does not change, there is essentially no obstruction to glue these numbers together and get a function from X to Z. On a given point, it extracts the Milnor number of the function, any function that I use to model X around the point and taking the Milnor number. And this thing is well defined because of this formula. So let me keep going on with my table. Sorry. So again, I have the local, the global, and the obstructions. So another example that something you can do when you have such a local model is to compute the cohomology of vanishing cycles, or more precisely, you can look at the perverse sheaf, PF. This is a perverse sheaf on U supported on the critical points, whose cohomology gives you the cohomology of the vanishing cycles of F. And one thing that you can do, or if you want to try to glue these sheaves globally, you're going to come across the following problem, is that if you add a quadratic variable to F, these perverse sheaves, they will be isomorphic, but non-canonically. And the reason is the following. First, if I add a quadratic variable, there is some theorem called the Thom-Sebastiani. I think I will not need this of the board yet. So that tells you that you can actually separate the two variables And this sheaf is actually a convolution of two sheaves. And now, let's actually make a simplest example. Let's suppose that Q is x squared plus y squared. So now, if I want to get an isomorphism between these two things, it's enough to get an isomorphism between P of x squared plus y squared and P of something I also have here, which is Pf and P of the zero function on a point. And essentially, these two things are isomorphic, but non-canonically. And the reason is that if I compute the cohomology of these, I get the cohomology of a sphere. Here I get the cohomology of the point, and I get Hn of S1 here. Sorry, I get H1 of S1. Here I get H0 of the point. These two things are both Z, but non-canonically it corresponds to choosing an orientation. So the obstruction is the choice. There is a choice here involved. And what around 2014, or 13 actually, Joyce, Brav, Bussy, so these names here is Brav, Bussy, Dupont, Joyce, and Sendroy. What they proved is that there is a way to solve this ambiguity here if the stack where you want to glue admits a square root of its canonical bundle, then the gluing exists. Okay, so there is some obstruction that comes from this choice of these orientations. But if you have the square root, you can solve these choices together, and you get a global perverse sheaf on the moduli that you care about. Okay, so now, very last example I want to give that will bring me to the subject of my talk. Another invariant that you can extract, which I will not have the time exactly to define here today, but there will be other talks where you will see this in more detail, is the matrix factorization category. So this is a two-periodic DG category, which essentially is given, I'm just going to write down the definition, is given by taking all the derived category of coherent sheaves on the zero locus of F divided by perfect complexes on the zero locus of F. The important thing about this category is that they vanish if and only if F is smooth. So, and you can try to do the same game here and glue them. So there was conjectures by Kontsevich and Söberman, and also by Toda, that it would be possible to glue these things. But of course, there will also be obstructions. So let me give you already some kind of obstructions that will appear. So if I add one variable and just the simplest quadratic form, these two things are no longer isomorphic even. So there is an obstruction about the dimension of your underlying smooth scheme. And the reason is that, okay, you have again this Tom Sebastiani, in this case proved by Prayagraj, that tells that you can separate the variables. But this piece here is not isomorphic. So this piece here is not isomorphic or equivalent as a category to the zero function on a point. So already you see that you also have to take care of some kind of obstructions. You have to match the dimensions, and there's troubles here. And essentially, what we did in the work with Olsztyn, so let me maybe write there's a theorem with Olsztyn, I'll write here. We'll start from there to write our theorem. Our theorem is that there are some obstruction classes that you have to trivialize in order to glue this. So this is around 2025. That there are two obstruction classes. So the first one lives in H2 et al. Of x with values in z. So x is my curly x. And the second one, gamma, lives in H3 et al. X Z2. Essentially, there are only two classes that you have to trivialize in order to be able to glue these categories. And if you trivialize these classes, then MF can be glued up to a certain nuance, is that up to isotopies of these G functors. So I will be more precise about this of these G functors. In a second, I will explain you where this nuance comes from. So just to give you an idea what this trivialization of this class beta means, the trivialization of this class is exactly what appears in the theorem of Joyce, corresponds to the existence of a square root of the canonical bundle. The trivialization of the class gamma, for the moment, we have a description, but it's not very satisfactory of what this means. So let me now start explaining you. So I want to explain, so all this, sorry, it's very important. In this theorem, x was derived -1 symplectic. The link means not that. Okay, or scheme. So what we would like to do is to extend this result to Artin stacks. So I'm going to give you today the first step to do this. But in order to explain you this step, I have to kind of explain to you a little bit exactly how we prove this result. So that's the second part of my talk, which is the proof device. So let me start by erasing this. Any questions so far? Yeah.
Gamma is a bit more mysterious. So how did you get it?
Oh, so maybe I can explain. Maybe I can explain the proof device. It was through the proof. Yeah. Essentially, I will explain the proof device, and then you will see where the class comes from. But essentially, it comes from the fact that you are gluing categories. So the stack, the gerb that is appearing here is Azumaya algebras. And actually, these are, because MF has Knorr periodicity, these are going to be two torsion Azumaya algebras. So this is the first classes appear in the pi1 of the stack of Azumaya algebras, two torsion. Essentially pi0 and pi1 of that stack. And actually, it was quite surprising for us. We're expecting to have, since we're gluing these kind of digi categories, we're expecting to have an infinite amount of coherences and an infinite amount of classes. But because of kernel periodicity, everything is too torsion. You kill all the upper classes, and this is the only thing that survives. Okay, so now let me give you an idea of how we prove this kind of theorem and how we can extend this. We hope to extend this to Artin stacks. So the key device that we're using is something we call the Darboux stack, which I will explain in a second. Is the moduli? We look at the moduli, the geometry of the moduli, parametrizing local Darboux models. Okay, so let me give you an exact, not exact, but at least an informal definition that from which you could deduce the exact one. So let's take X and omega to be a -1 shifted. And for now, I will keep two schemes or the Lee-Mumford stacks. So if you have such an object, you can look at the following functor. So I will consider X et al. To be the small et al. Site of my scheme or the Lee-Mumford stack. So objects will be maps. I can even consider et al. So S to be affine, but for now I'm not putting in notation. So et al. Maps to X. And from this up, I will consider the functor with values in infinity groupoids that sends such an S, like a local part of X, to the space of all possible identifications between S and some critical points on some function. So here is the following data I want to consider. So I want to consider S together with a nilpotent thickening to some U. U is going to be my ambient space. My ambient space in this case is going to be a smooth formal scheme. So there is something you have to accept if you want to do this stack. You have to pass to formal schemes. I can no longer work just with algebraic ones. I'm going to take a function on U. And essentially what I want is that the critical points of f on U to be S symplectically. So I want alpha to be a symplectic identification between S. So since this map is et al., I can pull back the symplectic form. I get the symplectic form here. And I want a symplectic identification between this and the critical points of f on U. So you can see that first, this is a complicated space. It's not just a set, because you can have many self-identifications of the symplectomorphisms here. I want to be rendering the symplectomorphism here. So now let me explain you why we take the formal schemes instead of just schemes. The reason is very simple. You want this to be a functor. So in order to have functoriality for this, by the way, sorry, I forgot to say something. We call this the Darboux, let's denote this, Darboux X to be this functor. So the functoriality, you see that if you have, let's just observe this, if you have S prime to S over X, all et al. Maps, okay? You would like to be able to pull back something like this defined on S to something like this defined on S prime. But you realize that if you have something like this defined on S, essentially this is a nilpotent thickening of S. And you would like to say that if there exists some nilpotent thickening here, such that this is a pullback. This is what the functoriality will mean. That it is a canonical way, given U, to construct some U prime. And the reason why we work with formal schemes and essentially with nilpotent thickenings, it's because of the nil invariance of the étale site. Since these things have the same reduced scheme, the étale site of S and the étale site of U are the same. So the moment I have an étale map here, there exists a unique étale map here. So the space of choices is contractible. Okay, not just connected, contractible. And this is what is telling you that there is a canonical way to define the pullback functor from local models on S to local models on S prime. So now let me give you a bunch of facts. The first fact is that this Darboux is a sheaf. So it's a sheaf on this small étale site. So what I mean is that leaves, sheaves, makes it all. Meaning if you have S and an étale cover of S, then you can use descent to produce from étale cover from some U on an étale cover to produce some U on S. And the other thing has to do with the way that this reframing contains the quadratic ambiguity. I can reformulate everything I said before just by noticing that there is another stack that is in the game. It's the stack of quadratic bundles on X. I can also see it, actually it's a stack that lives in the big site, but I can restrict it to the small étale site. And this stack restricted to small étale site acts on the Darboux stack. How does it act? If I have a quadratic bundle, and if I have a local model, I can produce a new local model just by adding the variables and the functions. And this remains a local model because this is a Morse function, so the critical points don't change. So something else we proved is that, and now I'm start to build until I come up to this theorem, is that one thing you can do is to look at the quotient stack of this action. So you are looking to Darboux models modulo this ambiguity. And these are sheaves, so I take the sheaf quotient. And I can look at the pi0 sheaf of this sheaf quotient because these are sheaves of infinity groupoids, right? So I can take the pi0 sheaf. And we prove that this is just a point. So in other way, if you see this in terms of sheaves, this action is transitive. Okay. So, so now a problem that we came across, and that is very well known to people working on the subject, I guess, is that this is non-zero. Okay, so this stack, although it is connected, it is not contractible. So let me give you an example to illustrate the kind of situations that we can have. And then the example also guides us to how to solve the problem. So the situation we can have is the following. Let me take U to be A2, but formally completed at 0. So this is just, if you want, this is puff of the polynomial ring with two variables. Okay, so it's a smooth formal scheme. And let me take the function to be, I don't want to make a mistake, x to the cube plus y to the 4. Well, it's going to be a complicated function, but it will illustrate what I want to explain. So one thing I can do is to consider an automorphism of this scheme. So I want to produce an element in pi1. So an element in pi1 is an automorphism of such a model. So let me consider the automorphism given by sending x to x plus y to the fourth, and sending y to the following very complicated formula. It's a formula that makes this work. I apologize for this. Whatever this is, this works. So this is I claim that this is an automorphism that preserves the function, and such that when I restrict to the critical points, to the derived critical points, I get the identity, not just as a scheme, but as a symplectic scheme. So this fixes everything, symplectic form and critical points. So it actually gives you an element in this pi1, and it is non-trivial, because the quadratic action does not kill this automorphism. You cannot stabilize the automorphism with the quadratic variable, so it survives there. So how do you get rid of this kind of problems, automorphisms? Because this will appear when you try to glue, right? The ambiguity is not just about having more variables, but about also having automorphism of such models. So you realize that you can make this automorphism isotopic to the identity by just adding a variable t here. When I by t. When phi is 1, you get phi. When phi is 0, you get the identity, and t lives in A1. So it's an A1 parameter family of automorphisms. For each t, it fixes the critical points. It fixes the symplectic form. So for each t is an element there, but gives you a family interpolating between phi and 0 in here. So let me state our main theorem now. Our main theorem is that if you kill all these isotopies, your quotient is not just connected, it's contractible. So if you take the Darboux stack and you kill isotopies, so essentially you identify maps which live in one parameter families, and you do the same for quad. Then you get stacks which are contractible. Contractible means this quotient is the constant sheaf with valued x in sheaves here. So that's what contractible means. It's an isomorphism of sheaves, so this is not next, this is the point. An isomorphism of sheaves between this quotient sheaf and the constant sheaf. So let me, before moving on to the Artin case, let me just explain you how do we use this to prove this kind of theorems, okay? And I will illustrate this using recovering Joyce's theorem, and it's very easy to modify to get this theorem. So what is going on? How do we prove this kind of theorems? So first thing important is that all the invariants are defined in my list before. They are defined out of this stack without any kind of ambiguity. So for instance, if I want to consider Joyce's sheaf, I will consider a map of stacks between the Darboux stack and the stack of perverse sheaves on X, seen as a stack on the étale side. So every time I have a local model, I will have the corresponding sheaf that lives on perverse sheaves on S, which is the value of what this stack on S means. perv sheaves X on S is perv sheaves on S. So this is a stack. So there is this construction that exists without any kind of ambiguity. And the Tom Sebastiani tells me that this whole map here is equivariant with respect to the quadratic action on one side and some action on the other side. So I have quadratic bundles acting on the Darboux stack. And then I have the perverse sheaves. And here I also have an action of something else, which is just the stack B mu2, classifying square roots of the structure sheaf. And the way this goes is I have a map of monoid stacks giving me a quadratic bundle. I can take its determinant. And I know that if I have a quadratic bundle that take its determinant, its square is a structure sheaf. So I have a monoid map. And the fact that this thing is equivariant is Tom Sebastiani. So I can pass to the quotient. And now, if this stack was contractible, if this was already a point, then I would just say that I have a section of this stack. But this is not a point, I told you, this is just connected. But perverse sheaves satisfy A1 isotopy invariance. They are motivic. Everything which is motivic does not see the line. So because they are motivic, so this map factors through the quotient mod isotopies. And this, I just told you, our theorem tells us this is contractible. So you get a section of this sheaf, which is a perverse sheaf up to some ambiguity. And what we would really like to have is a perverse sheaf. So we would like to say that the map, the section that you get here, lifts there. But the lifting is just given by quotienting further. You can look at a canonical map from the stack to the constant stack. It's a final map. And what you would like to say is that if this map factors through the upper one, then you have a lifting to perverse sheaves. So you're just asking that this composition is trivial. But this composition measures a class precisely where I identify my class beta. So this composition is actually beta. Okay? So if you try to do the same game replacing perverse sheaves by sheaves of categories, and B mu2 by Azumaya algebras to torsion, which is what happens when you get MF, well, you will see the same game here, but instead of having a B mu2, you're going to have a B of Azumaya. Okay, so that's so that's essentially what is going on, and that's where the class comes from. Okay, yes. Yes, so what I mean by this is that for any scheme, there is a pullback map from perverse sheaves to perverse sheaves on X to perverse sheaves on only 1 times X. This map is fully faithful. That's exactly what I need.
If the AMR of the invariance, we don't need any punishing cycle, but
it's the fact it's motivic. It's the fact that this is, it's the fact it's motivic. So, and that's why I said in this theorem here that for digi categories, because these are not motivic, I have to kill these A1 isotopy formulas. Okay. Okay, so now I have the last 15 minutes, I will explain to you why it's complicated to upgrade this story to Artin stacks. And I explain to you what we did. So I will tell you a simplified version of the story. I will not get into much technical details, but you already see why there is a problem. So part 3. So I erased here the definition of the Darboux stack. The Darboux stack, as was defined there, was something defined on the étale side of X as a functor to infinity group points. But if I have an Artin stack, I probably want to put here the smooth side of X. My atlases are going to be smooth maps, and I want to be able to pull these charts along smooth maps. But you see that if I have something like this, where everything is smooth, and if I have a local chart on S, I can no longer use the nil invariance of the étale side to say that there exists a unique thing here that will complete the diagram. So essentially, the first and maybe the only complication that appears in this story is the fact that this space, the space of such things, let me call it X, to be the space of such V, okay, where this, and these are fixed, this space is not contractible. So this creates a problem, is that there is no pullback from local models on S to local models on S prime. So there is no Darboux stack, at least in the way that we naively designed it in the first for étales, for the Ling-Mumford. So the key thing that we proved is here. Essentially, is that A1 homotopy invariant comes to help again. This space is not contractible. This space is A1 homotopy contractible. So, and this allows you to define a Darboux stack up to A1 invariants, which is good enough to prove the contractibility. And it's good enough for all the applications we have in mind. So let me keep here the key lemma. One of the key lemmas we proved is that X is A1 contractible. Okay. In other words, we can expect a Darboux stack, a pullback up to isotopies from local models on S up to isotopies to local models on S prime. So this stack, Darboux up to isotopies, will exist. Of course, this is not very satisfactory because you want to work with the Darboux stack before this isotopy business. And it makes sense. There is a way to define these things, which complicates a lot the story. But after working with this for several months, we are convinced this is the right way to do this, kind of to deal with this whole business. So before explaining the proof, I will give you just a sketch of proof of why this is true. Before giving this, I have some minutes. I just want to explain you how would you expect, how one can define something a bit better than just having up to A1 isotopies and still have something that resembles a stack. So what we can do, if you still want to have a Darboux stack before taking A1 isotopies, is to remark that, okay, I don't have a functor defined on the all smooth maps, but it's defined on étale maps. So I can see this as a partial functor. By this, I mean, if I look at this as a fibration, this functor as something fibered of the smooth side, I have Cartesian liftings for all étale maps. Okay? So what I mean, a partial functor is the following. So let me give you a definition. If I have just a functor between two categories, there is a definition which is, I say that it is, and I have a class of arrows in T. So I have a functor and some class of maps here. I can look at those functors such that will admit Cartesian liftings for all maps in the class W. And W in my case is étale, and in this case, T is X smooth. Okay? So this defines me a class of categories over T, which are partial Cartesian fibrations with respect to this class W. So if you put W to be all morphisms, then you get a Cartesian fibration, you get a functor, otherwise you get something a bit weaker. So actually what we showed, first, the Darboux stack is natural place, it's there. And not only this thing exists, makes sense, there is a way to define sheaves so that you can make sense of such a gadget being a sheaf. So the Darboux stack defined there is a sheaf. And the important thing is that the A1 localization also makes sense inside this framework of partial functors. So the claim is that although this is not a Cartesian fibration, when you pass to A1 isotopies, this becomes a Cartesian fibration. So this thing becomes a functor the moment you force A1 isotopies, but the construction has to be performed inside this setting. And the way to do this correctly, to say what we mean by sheaves, and actually the way that we found out that kind of puts together a lot of the stuff that is going on for Artin stacks, is to use a straightening procedure for this kind of vibrations, which we proved with the Félix Loubaton. It's just a lemma, we proved. And essentially it says that if you have any functor over T, there is no way this is going to be a functor from T to cat. But there is a way to see this as functors between a certain double category or infinity 2 category assigned to T and some other infinity 2 category. So these are functors between two double categories. One generalizes the Čech nerve, the Resk nerve of T with respect to W. I will say what this means in a second. If you ask me in the questions, I will give you more details. And the other double category is the category cat over delta n. So people paying attention will say that this is not a double category, this is not a double category, but there is one I can extract from this. Cat delta n. So these are both double categories. So double categories, if you don't know what these things are, these are just single objects in cat infinity. Okay? So just to explain a little bit what is going on here, there are two things. One, the Darboux naive is not even a functor, so you have to consider in some weird place. In this weird place, there is also a notion of a Grothendieck topology on this double category. So there is an infinity 2 category with a site structure. You can sheafify in terms of this sheaf on and in this infinity 2 category. And when you take the isotopy and you sheafify, you get what you expect here. And so let me just conclude before giving a sketch of proof of why that thing is expected to be contractible. Once you put all this formalism working in its correct place, what you find out is what you expected. Yes. So first I would have to tell what is this. Can you ask me the question in the end? No. Because the thing is here is that the level 0 is just a subcategory given by, is the étal site. It's just a subcategory with the classes in W. Level 1, you have the category of arrows in T, but morphisms are only étal. So you make sure that at every level, all the morphisms you authorize are étal. So there is no ambiguity. So the theorem first that we proved with Enum, we'll hope to post it on archive very soon, is of course what we expected, that for an Artin stack, this thing is still contractible, okay, as sheaves on a smooth étal side. But now, to conclude my talk, let me just give you an idea of why this space of extensions that I wrote there is contractible, okay? And the proof mimics something that we already had to do for the Mumford case. So first, you have to see that this space is non-empty. Sorry. This space is non-empty. And the reason why this is non-empty, it's when I mean non-empty, I mean locally non-empty. And the reason for this is because for the smooth topology, I can just assume that S prime is of the form S times some AN. So locally, I can assume this. And then for V is going to be U times AN also. So there is always a choice locally, which is of this form. That makes this work. So it's not empty. Secondly, it is connected. And the reason why this is connected, it's because if I have two V1 and V2 like this in this space, because these things are smooth, I can use the characterization of smooth maps, the lifting property for smooth maps, to construct one map this way and to construct one map this way. Okay? And because I ask that in my space of extensions, both things are pullbacks, this will force me these maps to be isomorphisms. Okay? So there exists always an isomorphism relating any two choices. So the question is about the higher homotopies that appear. And the reason why we can, so this is where the A1 invariant story shows up. Maybe I'll write. I'll conclude here. So the reason why this is true has to do with something we already used in the first work with Olsztyn. If this map is smooth, then we can always fix a connection on S prime locally that will allow us to identify this fiber product, the completion, sorry, of this fiber product with the relative tangent. So in the way this works, you can think of these endomorphisms of S over S prime, sorry, S prime over S, as a stack of endomorphisms. And essentially, we're fixing a connection. And essentially what we're saying is that if I have an endomorphism, it comes from the flow of vector field. So this is what is going on here. But because of this isomorphism locally, this now is a linear space. So it's a linear space. Any two choices, I can just give the homotopy that connects the two. So this space becomes contractible once I kill A1 homotopies. Okay, so this is something we already use in other papers. And this is what makes this statement work, that if I start with this is not a functor, I force isotopy invariance, and because of this fact, I get something which is a functor. And then I can go on and continue the proof. There is still some details I didn't mention. Let me just say, Yeah, maybe I'll stop here.
Okay, so other questions from the speaker?
I have two related questions. The first question is for derived schemes, you work with étale topology, but do you expect similar result for Disney-Beach topology?
I don't know. Because I don't know. Maybe we can discuss. I don't know.
I see. The second question is about the case for stacks. And if we consider a stack with good moduli space, then as explained in Hyunjun's talk, so we have a global critical locus description as a stacky ambient space.
Mm-hmm.
So do you expect that the Darboux stack itself can be defined for these stacks without taking the isotopy invariance by simply using the kind of formal stack given by the quotient of formal scheme by a reductive group?
But I don't understand. You still have an Artin stack. You still have. What are the what?
So the setup is when the stack admits a good moduli space.
Okay.
In this case, there is a kind of combined version of the Darboux theorem and alpha whole real local structure theorem, which describes stack locally, maybe Disney-Beach locally as a critical locus inside a quotient stack.
I still think you have to use this A1. The question is, do I still have A1 invariance to use?
Yeah. So my question is whether we can define Darboux stack in this.
I think so, because this automorphism I wrote there already exists on the formal scheme. It's very elementary. It will exist in the simplest kind of examples you can think of.
Mm-hmm.
So at least when I think of this example, it tells me that it doesn't matter if it's a stack or not a stack. We'll always have to force A1 invariance.
I see.
Yeah. Maybe. Yeah.
Other questions?
What happens if you work in, say, the smooth category or complex analytic category? Is there a corresponding story? I mean, do you expect one, I guess?
So let me think a second. You mean for C-infinity?
Infinity or analytic?
Yeah, so one of the things that we're using very deeply here, when we say that, for instance, this stack is contractible, also the quotient by quad is contractible, you're using Artin's algebraization. So you're using Artin's approximation. And yeah, so I don't know how that will transpose to the C-infinity setting, everything we do, because essentially, I didn't say, but the way we work with this stuff is you want to construct like a local model. Another way to see it is by taking a foliation and then taking the leaf space. And the reason, the thing that this exists as the leaf space exists as a formal scheme. And sometimes you have to actually take an algebraic model for this to show theorems. So I don't know if this would transpose exactly as we do. Maybe it would, but.
Questions? If not, then let's thank the speaker.